Okay, hi everyone, thanks for coming. Welcome to this week's seminar. I'll now pass you over to John, who's chairing the seminar today, and he'll introduce our speaker.
Yeah, it's my pleasure to introduce Pete Burgess. So welcome to people on Zoom and people on YouTube. You've both got mechanisms to ask questions at the end. So Pete, it says here, did his PhD in numerical stratigraphic forward modeling, and then he had a couple of postdocs. He's describing these informally to me. That one was on numerical modeling. I think that was with Burgess, wasn't it, Pete?
Was.
And then one with lots of rocks. So he has spanned the divide between numerics and actual rocks. He then was a lecturer for a while, and then he was a researcher and regional geologist in Shell. And then he returned back to academia, where he has been, to an extent, focused on coding models to better understand how strata form and what information and patterns they encode, or in many cases, perhaps don't. And he does insist that I tell all of you that he likes pandas and cats. So I have now told you that. So Pete, off you go.
That's the critical information, John. So yes, thank you for that intro. It's very good. That summarizes nicely. So I'm going to talk about these things: signals in deep water lobes, carbonate facies mosaics, why increasingly think narrow shelves are normal, and then a bit at the end about self-organized strata. And these things are for the most part linked by forward modeling, but if not, then they are quantitative stratigraphy. And these are all things that are puzzling me and have done for a while. So I'm not sure they puzzle everybody, but these are certainly stratigraphic topics that that I find puzzling and therefore interesting. So let's start with the first one: signals in deep water lobes. So this is all this is some published work that we're continuing now and building on. So let me just summarize kind of where we got to and with what's published. So we're using this stratigraphic forward model called lobite 3D, which is a very simple reduced complexity model of deep water sedimentation, basically. So deep water, mass flow, turbidity current sedimentation predominantly. And what we're doing is using it to explore how a sediment supply input signal is preserved or not as patterns in the strata. And here's some output on the right from the model, and the orange and yellows are basically beds of what would be sandstone deposited in a 45 odd meter thick section of strata, and the arrows are indicating thickening and thinning upwards trends in those beds. Okay, and this curve here is basically a signal. It's a sinusoidal variation in the size of the flows that go into the model. So what we're testing with this model run is to see whether the pattern of strata that we get reflects in any way, in any detectable way, that signal that's gone into it. Okay, and you can look just by comparing at a glance, really, these two. Obviously, this is in time. Time is on the vertical axis here. So I think it's about 2 million years of model time. You can see straight away that there's not a simple relationship there, and actually the reason for that becomes apparent when you watch the model animation. So this is a little extract of what happens in lobite 3D in this particular model run. The patches of color that you're going to see are flows of sediment down into the basin from up here where they're fed into the model, and you can see that what happens is they follow quite a complex distribution. They move around across the surface of the fan, and if you watch carefully, you can see there was a jump out to here, whereas predominantly before the focus of deposition was over here. So this effect that we're seeing is what we refer to as lobe switching, autogenic lobe switching, and it happens even in this really, really simple model. And it's the basic reason why that vertical section is not just a very straightforward, simple representation of the volume variations that you see in the input signal. Okay, and this we think is quite a realistic representation of what happens in real deep water fans. So what we're interested to know then is If we change that signal, we change its period and its amplitude, how does it get preserved in the rocks? And there's a fairly, I would say, it's not really complicated, but a slightly fiddly way of actually working that out. But the outcome is that for all of the model runs that are shown on this grid, so each of these grid squares is a model run with a particular amplitude and a particular period of oscillation of that input supply curve. If it's red, that's indicating that there's no detectable signal at the frequency or the period of the input signal, the supply curve that's gone in. If it's green, it indicates that the signal is strongly preserved. And the reason this particular plot is interesting, and I've got others that are quite a bit more noisy than this, so I've blatantly picked the best one, is that this shows that the signal is strongest when the amplitude is high and the period is lower values, or the frequency is higher, basically. So for a high amplitude, high frequency signal, you get it well preserved in the strata. Now, that isn't actually particularly surprising when you really think about it, because that autogenic lobe switching tends to chop everything up. So you might expect shorter signal intervals to be better preserved. But it is also, though, kind of the opposite of what everybody else has been, or many other people have been saying about what sort of length and frequency signals we'd expect to be preserved. The sort of concurrent view seems to be that it's the longer period signals that get preserved, not the shorter period. So this is a little bit of a surprising result. And for that reason, I've been really, for the last year, pretty much checking and rechecking and recoding the model to try and make sure that this isn't some strange thing that shouldn't really happen because it's unrealistic, and making some progress on that. And hopefully we'll be able to actually rerun all of these models soon with a new version of the model that we can test against the original. And I think if we start to see this result repeated, reproducibility is key after all, then we can have a bit more confidence in it. So this is the first thing that I wanted to talk about, signals in deep water lobes. The modeling might be suggesting that it's kind of different to what has been assumed in the past. Okay, next topic then is very different, but linked by a modeling approach. So carbonate facies mosaics. Let's talk about this. Here's the essential argument, right? And this is an argument that's been going on for quite a long time. And when I say it's an argument, it's rare that people directly argue over it. What tends to happen is that most interpretations that carbonate sedimentologists make follow the idea that carbonate facies are arranged in belts and migrate around under the control of sea level predominantly, right? Relative sea level perhaps. And what that would give you, and I'll show you this in a minute, is quite an ordered transition of facies as the strata stack. It would give you patterns, basically, because the forcing is simple, the geometry is simple. But what's odd about this facies belt model is that when we actually look at real systems, and I'll show you an example in a minute, they look quite a bit more complicated. They look more like what we refer to as a facies mosaic. So a patchwork of different types of carbonate sediment and carbonate producing organisms, so corals, bivalves, all the different things that make carbonate sediment, scattered in a more disordered way across the sea floor. And this, if you think about it, and we can explore exactly what it does do in a minute, if you migrate all of these different facies blobs around on the seafloor through time, you're going to get something quite different to this. And that's what this modeling that I'm about to show you essentially tests. It puts into an explicit numerical model these different options and tests how they behave. So here's the first one, right? Linear facies belts, and it's flipped round. I'm sorry, the model output is kind of in the other sense of, so in the previous page, in previous diagrams, you could see that water depth, this is landward, this is seaward. And so water depth is going from shallow to deep, and it's flipped round here in this case. So we've got it the other way around, but the model essentially is the same otherwise. It's basically got shallow water, deep water. The facies are arranged in these very linear belts. And when you oscillate sea level, what you get is exactly what you might expect. You get like propagation, retrogradation. That's these spiky patterns that you can see in here. They're all very regular, all very predictable, and it's integrating exactly as a textbook would tell you that they should. And if you actually take logged sections or vertical sections from different parts of the model, you can connect them up with correlation lines that are what we refer to as tram lines. They're very parallel, straight, not very complicated at all. So this is what you get when you use that tramline facies belt model. But the problem with this is when you actually go and look at real rocks, it's much, much more messy than this. Even if you try your best squinty-eyed correlation, you know, and geoimagination approach, you are unlikely to get anything ever that is as simple as this when you look at real vertical sections of carbonate rocks and try and correlate them. So what we're going to do now is try something slightly different. What if we model one of these facies mosaics? And the question really is then how to do that. So here's a very simple way to do it. You just define several facies patches. Let's assume there's something like a crudely defined circular type shape. There's 2 of this facies type, 2 of that facies type, 3 yellows, and so on. So you've got 4 different facies arranged in this initial condition as a sort of patchwork. There's bare seafloor between them where no sediment will be accumulating. If you now actually give each of those a trajectory and say, go this way, go that way, you send them off in different directions. And that's what this kind of multicolored lines plot shows. And they bounce around across this model. After 1 million years, you get something that looks like this. So they've all moved and some have accumulated together and some are still separated. This red is basically an area where, because of a fall in sea level, the sediment surface is subaerial exposed. If you look at what that model then produces, it produces something like this, okay, so here's a cross section. And we're talking about probably, I think in the model, it's 10 kilometers, which seems reasonable kind of scaling for what we're seeing. This is a chronostratigraphic diagram, in case you're wondering. So there's the white in there is lots of hiatuses between these different bits of deposition. So as a patch migrates away from a point, it leaves an area of no deposition behind it until another patch moves over the top. And the bottom line really is that when you do this, you end up with a much more, I mean, it's not tramline anymore. There are significant thickness changes. The things are still more or less parallel because there's no erosion in here that would really complicate things. But you can see that the timelines correlate facies of quite different types and rather unpredictable types. So this is much more like what we actually see in most carbonate strata, right? I mean, probably the reality is somewhere between these 2 examples that I've just shown you. Okay, so this looks like it's going to be quite a useful tool to explore this issue. How much are carbonate depositional systems arranged as belts versus mosaics in terms of how they behave through deep time? And the next step, which probably is quite obvious when you think about it, is rather than use an abstract kind of patch initial condition like this to start the model, what I'm going to do over the summer, if I have time to do it, is code up a initial condition that uses facies patches taken from actual mapped carbonate systems. So here's an example from Burgess et al. 2015. This is the east coast of Saudi Arabia, the Red Sea. It's a big carbonate platform with a shallow water platform top and reef margin. So there's a really nice facies mosaic defined in there. It's not quite, it's certainly not like this, but basically what I want to do is to try and take perhaps some small patches of that, start that as an initial condition, migrate the facies around using the same model, which I don't know what to call it yet, but possibly shelf stacker seems like it might be a good model name for it, and see what we get. Okay, so that's our next kind of way of looking into this issue of facies belts versus facies mosaics, which is most realistic. Okay, so that was topic number 2, which I think we're making some progress with, thanks to this bit of model, which incidentally is all based on Volta's law, if you remember that fantastic stratigraphic rule. So the next topic then, narrow shelves are normal. Let me explain what I mean by this. Okay, so we all know obviously what continental shelf is, and we see them all around the planet, and they're a ubiquitous feature of modern continents and maps, and in Google Earth now you can see them beautifully with the bathymetry data that's there. So these light blue areas around around North America, South America, you can see they vary in width. They have some quite complex structure in places that relates to tectonics. But interestingly, what I've always been intrigued by is the width of these shelves. Why are they as wide as they are in different places? And it turns out there are various reasons why that is. Okay. And most recently, I've been working on trying to understand how representative are these modern shelves of what we would expect to see through most of deep time Earth history. So in other words, the issue is, in the last 20,000 years, sea level has risen about 120 meters, right? The big Holocene, glacial-eustatic transgression, the North American, North Europe ice sheet melted, big volumes of water released into the oceans. It raised global sea level by about 120 meters. So much of this flooded shelf area is a consequence of that recent transgression, right? Now we know, though, that Icehouse climates are somewhat atypical in Earth history, right? I mean, certainly big ice sheets that can drive 120 meters of sea level rise in 10,000 years or so. That's pretty unusual. So that then begs the question, what were greenhouse shelves like? Okay, because these are effectively Icehouse shelves, Icehouse continental shelves. What did greenhouse continental shelves look like? Were they narrower, perhaps? I mean, that's the obvious hypothesis to test, isn't it? Because if these wide shelves are at least in part a consequence of that big Holocene transgression, if the transgressions were smaller, if the rate of sea level rise, the amplitudes of global eustatic rise were smaller, we would expect the shelves to be narrower. Okay, so this is the hypothesis that we now want to test, right? This cartoon kind of summarizes it, and the cartoons look very similar in many respects until you really get your eye in to see the differences. So there are two key differences. This is the Icehouse version, and it's got basically a flooded shelf here. If you look really carefully, you can see that sea level there's some white space there, which is the seawater, and there's some gray, which is basically muddy sediment that is covering the top of the shelf, and the shoreline is over here. Right, so that's an Icehouse type modern bathymetry in cross section for a continental shelf. Our hypothesis is that for greenhouse shelves, it looked quite different. The shoreline's out here at the shelf edge. There's very little or no flooded portion of the shelf. The cliniform top set, so this flat part of the cliniform here. So just to key you in, this shape is a cliniform, and there will be several other cliniform surfaces in here, you know, this wedge of sediment having prograded out from the margin of the basin. So there's no marine shelf on top of, oh, I've lost my cursor, no marine shelf on top of this cliniform. It's all basically terrestrial. So this is a slightly extreme, but perhaps, you know, reasonably typical example of what we might expect greenhouse shelves to look like, not marine shelves at all. The deltas would be out at the shelf edge. And people have been arguing this for quite a long time, but the real key question, I think, is what evidence do we have to demonstrate that this might be the case? So I've been working with a few colleagues from Austin. Ooh, hang on, let me just see if I can flip that. There we go. And we've been looking at about 10 different systems, some of which are greenhouse, some of which are Icehouse, and some of which are transitional. So in the Miocene period, for example, where we were, you know, ice sheets were growing and we were starting to get big glacial eustatic changes. So each of them is listed here, their location, their age, number of different top set measurements we've managed to make, because what we've done is we've taken apart mostly well log cross sections. We've identified the areas where we've got marine shale, and we've traced those landwards from their most seaward position to try and figure out how wide the shelf is. So these blue lines on here, for example, are some of these shelf units that we can see, and you can basically measure their width. And without going into lots of detail of exactly how we've done it pretty much directly from the stratigraphic data with as few assumptions as possible. And what we then get is a nice data set that looks like this. So this is basically a plot of those different systems organized by plotted age against normalized flooded topset width. And what that means is, in each case, we've taken the width of the marine flooded part of the topset and we've divided it into the total width of the cliniform so that we get a normalized width. And the reason we've done that is because looking back at these 10 systems, they're all quite different sizes. They vary quite significantly. So I think the Eocene Spitsbergen one is small, just a few kilometers across, whereas some of these others are pretty huge. Okay, so we've normalized it so that we can compare more directly. And when we do that, the essence of the result is that we see the mean normalized width for the greenhouse shelves is about 0.3. It's about 0.4 for the transitional shelves, and it's about, you can probably just about make out a red line in there, which is the mean. It's about 0.73 for the Icehouse shelf. So what we're showing, and it is pretty obvious when you really think about it, this is exactly what you would expect to find doing the analysis, and so no big surprises. But this is data, these are data that actually show that the Icehouse shelves are wider, substantially wider as a proportion of the whole length of the sediment system. Okay, so we're just writing this up now as a paper and trying to figure out what the kind of next steps for that might be, because there's a few interesting things this raises. I suspect that what we've met, so for example, I suspect what we've measured here in the greenhouse examples are probably the widest greenhouse shelves because they're the most obvious ones. When the shelf edge deltas were sitting out at the shelf edge for long periods, just aggrading, you would have no shelf and nothing to measure. So it may be that actually this, you know, if you took those into account, it would bring this average down quite a bit and we'd see even stronger evidence for narrow greenhouse shelves. And why does this matter? Well, it's a fundamentally different way to actually draw paleogeography through most of Earth history, right? I mean, paleogeographic maps would look quite different if there were no marine continental shelves. So that's just one, you know, pop geology point. But it also has consequences for how sediment gets rooted into deep water, which people have been arguing about for a long time. This would basically make the point that during greenhouse times, deep water systems are probably fed pretty consistently with sediment. There's none of this turning off during high stand and transgression because there weren't really any big transgressions, perhaps. That's what these data seem to be suggesting. So we'll see how it goes down in review when people look at it. And there's a few more things to explore because there are other controls on shelf width as well that we perhaps now need to go on and consider. Okay, so that's that. Next and finally, self-organized strata. So currently working a lot on this with Highway Z, PhD student in Liverpool, who some of you probably know. And we've been looking at some of the work of Alan Turing, actually, which is a lovely thing to be able to do because he was probably the first person to really talk about self-organization. But what actually is it? Here's a definition of spatial self-organization. It's the large-scale ordered spatial patterns that emerge from disordered initial conditions through internal interactions. So if you've got a system that has elements in it that interact spatially, for example, okay, they may start off disorganized, but because of the interactions between them, without any sort of external control, just the internal interactions, they can organize themselves into a pattern. And the classic example is, I think they're starlings. Is it a murmur of starlings? I think that's what this is. They're the classic or the most spectacular example that I know of anyway. So there's no leader bird in here. There's no Boris bird that's telling everybody what to do. All of these birds are simply following a very simple instruction: fly close, but not too close to your nearest bird. That's essentially what they do. And the fact that they all follow that instruction means that they self-organize into these flocks, okay, which is pretty amazing actually when you think about it. But this is a lovely example of spatial self-organization. But there are lots of examples in depositional systems as well. So here's one from reef systems on a reef in the Gulf of Mexico. And here the corals organize themselves into these they're kind of quite complicated to describe, but definitely patterned systems. right? Another example of self-organization. In this case, it's competition for food, for space, protection against predators, you know, the usual things that organisms do, and they organize themselves accordingly, right? So in all of these cases, through no external forcing, there's nobody saying, you know, do this, do that, and issuing instructions. There's no sea level curve driving this. Patterns emerge just through internal interactions. So what Highway and I have been doing is exploring this happens or might happen in carbonate depositional systems. And what we is that it probably does happen. Okay, now let me show you the first example. So this is a model of a carbonate platform where sediments accumulating. What you can see is horizontal distances and then elevation in meters. This is the platform top, right? This blue patch. And at the moment, it's all below sea level. It's about 2 or 3 meters of water depth out here. And this is essentially a shoreline at the edge of the carbonate platform. And what's happening in the model is sediment is being produced by carbonate producing organisms out here and then transported onshore and stuck onto the edge of this shoreline. Okay, so what's going to happen when we let that run through time as forward models do? What happens is this. You can see that the islands, the shoreline progrades, becomes detached from the area behind it, and a new subtidal or a new zone of water forms behind it. And that's because this area here is sheltered from any further sediment transport. So let me just show it you again. So the islands prograde. They get out to the edge of the platform and stop because their source of sediment's cut off. And you can see the island, the shorelines arrange themselves into this series of islands that have got a more or less equal spacing. And the reason for that, and that probably is the first indication that we've got self-organization going on in this system. And the reason for that happening is it takes a certain amount of width of subtidal zone. So this is the subtidal zone here, the zone on the carbonate platform that's got water depths that are always, well, it's always flooded, basically. It's never actually exposed by low tide. So we say subtidal zones. So those subtidal zones feed sediment onto the shorelines, and it takes a certain width of subtidal zone to make the shoreline behind it prograde. Okay, so this is where the self-organization comes in. There's an interaction between the progradation of the shoreline, formation of an island, and the width of the subtidal zone that forms it. And the consequence of this, in terms of rock record, are these lovely sort of blue, green, yellow stripes that you can see in the side of the carbonate platform here. So here we've got about 30 meters of accumulated carbonate strata. And what you're seeing is a series of shallowing upward units of rock in here, going from blue, which is about 10 meters water depth, maybe a bit less, maybe, I don't know, probably more like 2 or 3 meters water depth, into yellow with patches of red. And these are basically little shallowing upward cycles formed by these prograding islands. And these are pretty similar to what are often interpreted to be present in carbonate platform strata in lots of ancient examples. So here's an example from the Tremp Basin, Upper Cretaceous carbonates in northern Spain. And these are allegedly or interpreted to be organized into cycles, often with some subaerial exposure at their top. What we're actually demonstrating with this modeling is that rather than this being generated by sea level changes, which is the pretty typical interpretation, you know, sea level goes up, sea level goes down, it generates these shallowing upward cycles, exposes the top. We can generate something actually very similar and nicely ordered, and we can quantify all the order that's present in these strata by this self-organizing mechanism, right? So it begins to demonstrate how self-organization might be acting in carbonate systems and perhaps other depositional systems too, to actually generate things like cyclicity, which is something that we've always, you know, been interested in strata. Okay, so that's one example of self-organization. Let's go on to the next one, which is similar in some ways, but a slightly different type of carbonate system. Now we're going to start talking about, rather than autocycles and a nice, healthy, coral dominated kind of typical carbonate platform top. Now we're going to start talking about microbial lights, which are quite a different kind of carbonate rock produced by trapping of sediment and in situ production of sediment by microbial communities. Okay, and here's an example of what they look like from the lower Cretaceous of the Purbeck group in Dorset. What you can see if you look carefully, nicely laminated rocks, which are kind of the background sedimentation in this carbonate setting. But then you can see this like quite messy kind of, it looks almost like a brain or cauliflower structure in there. Look, if you see, these are the microbial lights. This is specifically called a thrombolytic texture. So these are in situ growing carbonates produced by precipitation from microbes, essentially. Okay, now the reason we're interested in these from a self-organization point of view is there's a fair amount of evidence that these produce patterns, right? So what we're trying to understand with the forward modeling is, okay, what kind of patterns can we replicate in a model, and are they self-organized? What kind of evidence can we define to show they're self-organized? And Highway's done a lovely job of modeling both of these systems, but this is particularly lovely. People, if you're a carbonate person and you see models of microbial lights, everybody tends to get quite excited. But let me just show you the oh, that wasn't supposed to happen. Hang on, I wanted to slow the slide. Let's see if that'll play. There we go. So what you need to watch for here is green is background sedimentation and blue is the microbial lights. And what you can see emerge out of this model run, let's run it again. It starts off at the beginning with a pretty random surface. The elevations are pretty random and the distribution is mostly blue, right? But it's basically organizing itself here into a series of quite linear bifurcating ridges. All right, and this is happening because in the model, which incidentally is called Stratigraphic 3D, which is, you know, another pun, of course, we've got an interaction of suspended load sediment transport and in situ microbial light aggradation. So I'm not going to explain the details because it would be a bit dull to go through all the details of the model for most of you here. It's the kind of thing we would do with, well, Highway did a lovely job talking about it at the Carbonate Forum a few weeks ago. We won't going to talk about it here, but all you really need to know is that there are interactions between sediment production by the microbes, sediment transport, sediment trapping, and they're basically leading to the emergence of these ridge-like platforms in the platform top. So let me just show you, I think, a couple more slides that elaborate on that. So we can explore that a little bit more by running a few different models now. So I've just shown you one animation, which is from one model with a particular set of parameters. What I'm going to do now is to try and explore how that mound or ridge distribution develops under slightly different situations from random initial topography. We've got 4 models, and this little table shows what's in them. So the first one has got no sediment transport at all. It's very simple. It's just in situ production by the microbes. And then the last one, model 4, is the most complicated and has got pretty much everything in it, right? So we're seeing an increase in model complexity from 1 to 4. So it's a simple experiment to test what happens when you put more and more complexity into the model, more and more processes that can interact, right? And we're starting off with this initial topography, which is, it's about 0.5 meter relief. The blue bits are deep, the red bits are shallow. It's all just below sea level, so we can accumulate sediment on it. But that's a random initial surface, right? It's slightly smooth, so not completely random, but there's certainly no order or pattern in that initial surface. And yet, when we run the model, what you can see happens is, for the really simple case, not much. We just get mounds growing controlled by that initial topography. But when we start to add sediment transport and the interactions that are, you know, that typically do lead to self-organization, by the time we've got all those together, we end up with this beautiful pattern of almost like Seif dune type bifurcating linear ridges. And this is, we think, pretty much a self-organized system. Okay, and also importantly, what we can do is we can compare each of these models with examples from modern carbonate microbial light systems and say, oh yeah, this one has got definite geometrical parallels with, you know, a depositional system that we can observe. So that's an important test to see that actually this is quite realistic, that we're actually modeling things in a more or less, well, yeah, realistic kind of way. It's not completely crazy, off the wall, unrealistic, you know, model. It does have some connection to what we actually observe in the real microbial light system. So the final point here is then what we really need to do next is basically work out how much pattern is present in the strata that we produce. And this is something that is a theme throughout all of this self-organization stuff. To demonstrate that it's organized and it's self-organized, you need to have some really good metric to characterize the organization. But it turns out that's actually pretty tricky, right? It's quite a tricky problem, because in broad terms, there are common elements to the way things organize, but in detail, it differs. So coming up with one single metric and measure and one algorithm that will always give you a robust and useful measure of self-organization in these systems is pretty tricky. And Highway in particular has been doing lots of hard work trying to work out how to do exactly that. And I think we've made some progress, enough that we can probably start to write up some of these results. But I think further pursuit of that kind of metric for self-organization is, I think, going to be a key research aim. And then, of course, we can apply it to lots of different stratigraphic examples and start to really search for this effect in other systems, maybe even systems that we can't model. Okay, let's see. That's just under 40 minutes and I'm done. So there's a summary slide. And if anybody has any questions, go ahead.
Yeah. Thanks very much. So we have 4 topics. I think we take questions from Liverpool, and then if YouTube people have questions, we can come to them. I'm just trying to adjust my screen so I can see if anyone's hand is up. I am failing in this at the moment. Does anyone want to just shout out questions then? Yeah.
Hi, Pete.
Hey, Leo.
Hey, yeah, so particularly the last part there is really interesting, just looking at the self-organization stuff. I wonder, do you see this in other things in geoscience? So things like thrust belts and like more large-scale tectonic features, or is this mostly for just the sedimentary?
That's a good question. You know, I think, I'm just trying to cast my mind back. I think people have argued that there are elements of self-organization present in big scale geomorphic things like drainage networks and so on, right? I'm not sure about thrust belts, actually. I don't know about that. I don't think I've heard people say, talk about that. I think, well, Dan can tell us more about self-organization in fault systems. I think I have heard people suggest that, at least as an idea, even I don't know what the evidence for it is like. But I mean, it's, you know, you probably know, I mean, there are lots and lots of sedimentary examples, and they often have things in common. So that island progradation model is actually not dissimilar to aeolian dune systems and, you know, ripples on a beach. I mean, the physics is actually very similar, and it would seem probably a little bit scale independent, perhaps.
You want to follow on that, Dan? Because actually I could say some random stuff about that, Pete. Would you like that?
Yes, we can see how random it is, John.
Well, I mean, vague memories based on even the initial work in, for example, acid, says that when you get imbricate systems, I mean structural imbricates, one thrust on top of another, they're quite regular in their thickness. So you think there's a length scale there. And I'm also thinking out loud about other structural geology phenomenon, like the spacing of crenulation cleavage.
Yeah.
There was another one, but I've forgotten it already. But actually, the world is full of patterns, isn't it, Pete? And I don't have the answer to how you decide which bits are self-organized and which bits are organized by some mightier force somehow.
So the distinction is often quite difficult, actually, because it can be quite nuanced. You know, where in the system does something need to be acting to be autogenic versus allergenic, as the terminology goes. But the other issue is, and this is certainly been a big issue in sedimentology and stratigraphy is people love to see patterns even when there just really are not any present. So, I mean, the first step I always think is some robust quantitative evidence that you really are looking at something patterned, by which I mean something that is highly unlikely to occur by chance, right? But that then gets a little bit complicated, because in the end, when we talk about chance, what we're typically talking about is just complicated, right? And so the distinction there is not necessarily either as straightforward as it seems. So this is one of the reasons why I've always been so interested in this topic. It's just you know, it's a really absorbing thing to try and figure out how we even make simple definitions in some cases, so that we can make sure we're talking about things with proper evidence and not just saying, oh yeah, you know, it's cyclical, which people say about strata all the time, even when it's rampantly not.
Interesting. Well, I mean, actually, the words autogenic and allergenic are specific sedimentology terms, aren't they? But you've made me realize that actually there's quite a general principle there, isn't there, really? Yeah.
So you know, I don't think they are just sediment. I mean, they just mean self-generated and externally generated. So I mean, I think you could use that terminology for pretty much anything. I mean, they're most typically used in sed and strat, I suspect, but I think they would apply across science.
Do we have more questions? I haven't got my screen so I can see anyone's hand up, so you'll just have to shout.
Can I ask a question, John?
Yeah, Dan, go ahead. Yeah.
Thanks. So Pete, I think this is just a point of a clarification, because I don't quite get this in my mind with regard to the stuff you talked about on the width of marine shells. So if I understand this, you're saying that you get wider marine shells when the Earth's temperature is lower. Is that right?
So when there are big ice sheets present,
yeah,
and we're in an icehouse climate, so that there's been a few points in Earth history when that's been particularly the case. So the end of the Carboniferous into the Permian,
yeah,
the end of the Ordovician into the Silurian, and obviously the last couple of million years. At those points, the ice sheets wax and wane, and when they melt, you get these big flooding events that generate wide continental shelves of the type that we see today. And what the analysis that we've done indicates is that those marine shelves were probably much narrower at times when there weren't big ice sheets present, so in greenhouse climate settings.
So that seems still a bit back to front to me. So if you've not got many ice sheets, sea level's higher, so therefore you'd have wider shelves.
But the thing is, you see, I see what you mean. But because you've not got big fluctuations in sea level, all the rivers basically build out to the shelf edge. Because this was kind of probably one of the things that people realized that led to this debate, right? If you look at the Mississippi River, it's built out almost to the shelf edge over the last 10,000 years. So since that Holocene transgression, it's basically built a shelf edge delta pretty much, right? So but it's a big river, so it's not, you know, typical of the global mean. But when you actually look at the sediment supply from global rivers, most of them can build a shelf edge delta and essentially fill in that marine portion of the shelf in a few tens of thousands of years. So if you don't have big sea level changes going on, those shelves will fill in and you'll just end up with a terrestrial coastal plain and not a flooded marine shelf.
So the interaction of sea level and the rivers is basically self-organizing itself.
Oh, well.
So really the width of the shelf is more to do with the fluctuations, the shorter period fluctuations, rather than whether or not you've got the fluctuations are a product of the ice sheets, the present.
Exactly.
Okay.
So I should have explained that better, Dan, but that's the point, that in an icehouse climate, we expect big fluctuations in global sea level. In a greenhouse climate, those fluctuations are going to be much less, right? And that's the key thing that's driving this difference.
Brilliant. Thanks, Pete.
I have a question, if that's okay.
Yeah.
Thanks for a great talk, Pete. I was just wondering a bit about your numerical model. Like, do you have like physics-based equations that define that define the internal interactions in your different self-organization problems that you're looking at?
Yeah, so you know, it's all pretty simple. They're all reduced complexity models, but yes, they're all based on basic physics. So, for example, we would calculate the flow, the velocity of flow, and calculate from that, or estimate from that a shear stress, and from that we'd say, okay, so we can pick up this much sediment, or we can't carry however much sediment is in the water column, so it's going to be deposited. It's simple rules like that. And you know, in the fan model, it's transport things down slope until you reach a slope that is low enough that you can begin to deposit. I mean, they're very simple models, but yes, they are physics based, because otherwise, you know, obviously they'd be even more unreliable than models always are, right? You want them to be based in simple physics.
Okay, thanks. Again, do you have like a reduced flow equation, or do you fully solve for the flow?
Oh, it's always reduced, and probably the main reason for that is because if you try and do you know, full 3D flow calculations or even 2D flow calculations, and you then try and run a model that actually simulates several million years of deposition, you know, it takes a crazy amount of computer time to do that. So this is another reason why we really want to try and keep them simple. So I think, I mean, this has always been my tendency anyway, to use the simple models. There are much more complicated versions out there. So for example, there's a model called Delft 3D, which does fluvial shallow marines, and that's got, you know, much more sophisticated representations of the physics in it. But it's hard to run that model for millions of years because, you know, it just takes a long time. It takes a lot of memory and so on. So it's a balance really between how much complexity you put in and how much time you really want to represent in your results.
Okay, thank you.
So, anyone else? Because I've got another question. Sounds like me. So actually, Pete, following on from Caitlin's question, the migration of your carbonate patches, that sounds like a different kettle of fish.
Yeah.
I don't know how much that can or is physics based, actually.
So yeah, that's an interesting question, John. I mean, in reality, it's biophysics based, I suppose would be the best way to put it, because most of those patches have got some biological element to them, right? In carbonate systems, they're carbonate producing patches, and they're a bunch of organisms that do no, but exactly what rules and so on and what physics is causing them to migrate, I don't think we know an awful lot about that. I mean, there's a few examples. So for example, ooid shoals on the margins of the Bahamas platform. We've got a good understanding of the physics, how they migrate laterally. But in most of the cases, I don't think we really do, right? So I mean, this kind of modeling is really at the level, what happens if these kind of mosaic patches migrate, and we're not really worrying about the details at that point of how that happens. We're just saying what happens if they do. And I think even that is a bit of a step forward at this point for carbonate sedimentologists. Sometimes you can get away with being really, really simple because, you know, I think that the interesting thing about carbonate systems is people haven't really thought about them as in a sediment transport kind of way previously. They tend to think about in situ production by, you know, coral reefs and things like this. They don't think too much about how things move around on the platform top. So there's definitely something to explore there, I think.
So, Caitlin, are there any questions on YouTube?
No, there's nothing on YouTube at the moment.
Okay, well, we've got a bit more time. And I do have another question. Does anyone else want to ask a question before I ask another? Well, Pete, I mean, so just, I was thinking about two bits of your talk tied together. So I'm just sort of, this is random again. So you're explaining that because we're in an ice house, you've got wide continental shelves. But then I was thinking in relation to your carbonates, well, isn't that wide, shallow shelf just a nice place to grow coral reefs and such like? In which case, is there something non-uniformitarian about the present day carbonate production in the world? I mean, is there anything to explore there?
Yeah. I mean, I think that there definitely is, right? So when you look at most modern carbonate systems, they're in a mode that we would probably, that carbonate stratigraphers would refer to as catchup, right? Not ketchup, catchup, because they're trying to produce enough sediment to get back to sea level, right? And this is not always the case. Some platforms are shallower than others, but there are quite a few that are in this kind of like bucket morphology, as we call it, and they're trying to now build up a sediment back to the sea surface, because that's what carbonates will tend to grow and accumulate towards. So that's definitely the case for some platforms. But, you know, I mean, you're hitting on an interesting point there, because other platforms seem to have survived that Holocene transgression or evolved since, so that they're now within a few meters of sea level. So, I mean, it kind of depends a little bit. Yeah, it's a little bit complicated, because it kind of depends what the physiography looked like before the sea level fall. And then, do you see what I mean? So I think probably in some cases, you've simply had platform tops that were exposed above sea level for a long time, and then it's the very, very final stage of global sea level rise that's flooded them. So they're now actually in pretty shallow water, and they're, you know, happily accumulating. But when you look at the continental shelves, if there's any kind of slope on them, then obviously that's a slightly different situation, and there's some carbonates left in quite deep water that are more in this catch-up phase. So sorry, that wasn't a very organized answer, but it's I mean, if you look globally, that distribution will be quite complicated, I suspect. You know, some deep, some shallow, some keeping up, some catching up.
Thank you. Okay, so I'm not hearing any questions from Liverpool. Is the YouTube chat still we've still not got anything there? So look, I think now is the time we can reconvene in Gathertown. So I mean, Pete, thanks for that very interesting talk. Nice to have 4 little topics each that you can kind of get some overview of. And so thanks very much. Thank you to the YouTube audience and the Liverpool audience. And I'm going to nip into Gathertown now.
Yeah, see you there in a mo.